In this lecture video, we're going to review three important and related topics: random variables and their distributions, sampling distributions, and the central limit theorem. Now let's recall the general procedures for making statistical inferences. First, we obtain a sample from the population being studied. We study the sample. We summarize the data in the sample using the descriptive techniques that we learned in Module 1 for the purpose of gleaning useful information about the population. And then we generalize results to the population. Now there's a catch. The sample carries with it information about the population for sure, but this information is incomplete. There's just no way that a subset of a population can contain all the possible information about a population. In addition, variability exists from one sample to another. So this variability and lack of information leads to uncertainty. Now, inference and decision-making, this process of generalizing from the sample to the population, is necessarily conducted within the context of this variability and uncertainty. So the question is, how do we formally include uncertainty and variability in the decision-making process? What is it that makes this process valid? And that's where probability comes in. Now, probability is the means by which statistical methods account for the variability in the samples that we obtain from a given population and the resulting uncertainty regarding the characteristics of that underlying population. Now, statistical procedures give not only an answer to a question, but they also measure how confident we can be in that answer. So that's really one of the most powerful things about statistics, is that we not only get an answer to a question, but we get a measure of the reliability of that answer. Now let's consider some definitions and concepts associated with probability. The first, a random experiment. Now this is a process or procedure possessing a well-defined set of outcomes, which cannot be predicted with certainty on any given trial of an experiment. An elementary event is a possible outcome of the experiment. Now, the sample space of an experiment is the collection or set of all elementary events, that is, all possible outcomes of an experiment. And then a composite event, usually just called an event, is a collection of elementary events. Next, let's think about the concept of a random variable. So a random variable is a function or rule that assigns a numerical value to each outcome of a random experiment. So to each elementary event of a random experiment, a random variable maps that or assigns to it a real number. Now, we can categorize random variables into two broad categories. The first would be discrete random variables. A discrete random variable is a random variable that can take on, at most, a finite or countably infinite number of values. The probability mass function, or PMF, of the random variable gives the probabilities associated with each outcome. And the kind of the standard notation for a PMF is lowercase f or lowercase g or h or something like that. Next, we have the other type or broad category of random variables, and these are continuous random variables. Now, a continuous random variable is a random variable that can take on any value in one or more intervals on the real line. Associated with a continuous random variable is what is called a PDF, a probability density function. Again, and also denoted by lowercase f, for example. This PDF does not give probabilities associated with outcomes, but it gives what are called density values. In order to find probabilities associated with a continuous random variable, what is required is to integrate the PDF over the appropriate interval that corresponds to the event of interest. So again, we've got two broad categories of random variables: discrete random variables and continuous random variables. When we're dealing with discrete random variables and the corresponding PMF, the probability mass function. Again, the PMF gives probabilities associated with individual outcomes, and to find probabilities of events, we would typically use summation, summing up the values of the PMF for the outcomes that comprise the event of interest. On the other hand, with continuous random variables, we get probabilities involving random variables by integration. Now, once we've defined random variables and talked about their distributions, we can start talking about characteristics of those distributions. So let x be a random variable, either of the discrete type or the continuous type, and denote the sample space of the random variable x by script A. And so the sample space, again, is the set of all possible values that the random variable x takes on. And then we'll denote by lowercase f either the probability mass function, the PMF, or the probability density function, the PDF, depending upon whether x is a discrete random variable or a continuous random variable, respectively. Now, the expected value of the random variable x, which is denoted using this notation here, we can see this e of x, so this is read the expected value of x, and it is defined in the following way. And it depends on if we're dealing with a discrete random variable or a continuous random variable in how we would calculate it, but the underlying idea is exactly the same. So don't let this difference in notation throw you off. Expectation, or the expected value of a random variable, is the same regardless of whether we're talking about, conceptually the same, whether we're talking about a discrete random variable or a continuous random variable. And so let's look at what the expected value of x would be if we're dealing with a discrete random variable. And so in that case, lowercase f would be the PMF, the probability mass function, for the random variable. And notice that what we're doing here in this calculation, which defines expectation for a discrete random variable, is that we are summing. So we have the summation operator, and we're summing over all values of little x in the sample space of capital X, the random variable x. And again, that sample space is denoted by script A. So this is just a way of saying we're going to add up the terms in the sum for all values of x, little x, in the sample space of the random variable x. So what are the terms in the sum? Well, we can see that they are products. The product of x times f of x. Again, x is a value from the sample space, and then f of x is the probability associated with that outcome. And so this is a weighted sum of the values in the sample space of x. And the weights are the values of the PMF, the probabilities. Now, the sum of the weights, the sum of the PMF values over all values of x in the sample space is just 1. So not only is this a weighted sum, but this is a weighted average. And so we can then interpret, or we can see that what the expected value of x is, it's a weighted average of the values in the sample space of the random variable, the weights being the probabilities associated with each value. Now, if x is a continuous random variable, the operation for how we would calculate the expected value of x is necessarily different, because we have an infinite number of values, in fact an uncountably infinite number of values in the sample space of the random variable, because remember, a continuous random variable can take on any value in one or more intervals on the real line. And so we're not able to use summation to add things up over that entire sample space. So what that becomes then, if you try to do that, it becomes really integration. So that's what this represents. But again, don't let that notation throw you off. The idea is exactly the same. If you've had calculus, then this may make sense to you. If you've not had calculus, don't worry about it. all right, because we're not going to actually have to do this, but this is the definition for the expected value of x when x is continuous. The bottom line is that regardless of whether we're talking about a discrete random variable or a continuous random variable, the expected value of x is a weighted average of the possible values that the random variable x can take on. Okay, now let's suppose we have a function of x. Instead of just x itself, we have some function of x, and so we'll denote that function by lowercase g of x. All right, and so this is we can think of this as a transformation of the random variable x. Now, when we calculate a function of a random variable, the result is itself a random variable. All right, and so g of x is a random variable, and so it makes sense to talk about the expected value of g of x, just like we talked about the expected value of x itself. So, the expected value of g of x, which is denoted as you would probably expect here, the e of g of x, and so the expected value of x, and it's defined in an analogous way to what we saw for the expected value of x itself. In fact, the expected value of x is just a special case of this definition where g of x is the identity function. So the expected value of g of x, if x is a discrete random variable, then g of x will also be a discrete random variable. And so the expected value of g of x would just be the sum, x going over all values in the sample space of x, of the product g of x times f of x. And again, f of x is the PMF of x itself. All right, and so we can see here that the expected value of g of x is just a weighted average of the values that are taken on by g of x, the weights being the probabilities associated with the individual values of x. And then if x is continuous, then we obtain the expected value of g of x by integration. All right, so we would integrate over the entire real line g of x times f of x. Okay, but again, if you've not had calculus, don't worry about it. We're not going to be doing this, but again, I'm just including this for the sake of completeness in the notes. All right, now that we've defined expectation, the expected value of a random variable, and more generally, the expected value of a function of a random variable, we can start talking about characteristics of distributions that are important in the study of statistics. And those characteristics are defined using expectation. So we're going to first talk about the expected value or the mean of a distribution, the expected value of a random variable or the mean of its distribution. We can speak of it in either way. So let x be a random variable with sample space script A, and then also either PMF or PDF, lowercase f, again depending upon whether x is discrete or continuous. Now the mean of the distribution of x, which is also the expected value of x, we can define in two ways. Mu sub x, lowercase Greek letter mu, and we can subscript that with the letter of the random variable if that's helpful. This is one piece of notation, one way of denoting this. The other is, as we've seen, the expected value of x. Now, if we're speaking about the mean of the distribution of x, oftentimes we'll use this notation, mu of x, all right, so that we are very clear what we're talking about. If we're talking about the expected value of the random variable x, then we might prefer to use this notation. But really, those are interchangeable, all right, and we can use either one, which helps make the discussion clearest. Okay, so the mean of the distribution of x is defined to be the expected value of x, and so we've seen how to calculate that a few slides back. All right, so that is the definition for the mean of a distribution. Now, the mean of a distribution has as an interpretation it's the center of mass of the distribution. And so if we were to think about drawing a graph of the distribution of a random variable, and then under the horizontal axis putting a fulcrum, and then sliding that fulcrum back and forth so that the horizontal axis with the distribution on top of it either tilts to the left or tilts to the right depending upon the position of that fulcrum. Then, like a teeter-totter, then the horizontal axis would perfectly balance. The distribution would balance on top of that horizontal axis when that fulcrum is right at the location of the mean. All right, and so that is why the mean of a distribution has as the interpretation, it's the center of mass of that distribution. All right, next we have the variance of a distribution. So the mean of a distribution is the balance point or center of mass of a distribution. It gives us a measure of where, it's a measure of location, right? It gives us an idea of where the distribution is, in particular where the balance point is. The variance of a distribution is a measure of how spread out or dispersed the distribution is. All right? And so let's define this. This is also defined in terms of expectation. So the variance of the distribution of x will be denoted in a couple ways. Again, sigma squared sub x is one way to denote this, and then var x, var of x, is the other notation that is commonly used. And it's defined in terms of expectation in the following way. Now, by defining it in terms of expectation, we no longer have to have different formulas depending upon whether we're dealing with a discrete random variable or a continuous random variable. That difference, that differentiation, is included or contained within or encapsulated within the definition of expectation itself. So we don't really have to make that distinction anymore. And that's one of the advantages of using expectation to define these quantities. So the definition formula for the variance of a random variable x is that it's the expected value of the squared difference between the random variable and the mean of that random variable, the mean of its distribution. Or we could, again, we can write mu of x as the expected value of x, and so we could speak of the variance as being the expected value of the square of the difference between the random variable and its expectation. So that is the definition for variance. If we remember that expectation is an averaging process, then we can tie this back to terminology that we used in the context of descriptive statistics when we said that the variance in general, in words, is the average squared deviation about the mean. And so we see that this concept, this is the same exact concept. Remember, expectation is an averaging process, and so we can think of the variance as the average squared deviation about the mean. All right, so that's the definition formula, right? It's written in such a way, expressed in such a way, defined in such a way that it matches our verbal description. But then we can also come up with a computational formula, and this computational formula is equivalent to the definition formula in the sense that you'll get the same answer regardless of which one of these two formulas you use. All right. Now, to get from the definition formula to the computational formula, we would have to use some properties of expectation, but it's a very, very simple derivation. We're not going to go into it, but it's not that hard. But the computational formula for the variance is that it's the expected value of the square of x, so the expected value of x squared, minus the square of the expected value of x. And because the expected value of x is also mu of x, we could write this as the expected value of x squared minus mu squared, right? So we could write it either way. Now, the reason that this is perhaps easier to use is that we don't need to take the difference between every value of x in the sample space and the mean and then square that in calculating the expectation. All we have to do is do a difference one time. We first find the expected value of x squared. Well, that's second. We would first find the expected value of x. All right, then we find the expected value of x squared, and then we calculate the difference as shown here. The expected value of x squared minus the expected value of the minus the square of the expected value of x. And so again, the variance, this is a distributional characteristic, and it quantifies how spread out or disperse a distribution is. Now, the more spread out a distribution is, and I'm thinking graphically now, I'm thinking about maybe a normal distribution or any kind of distribution really. All right, but the more spread out that distribution is, the greater the variance, and vice versa. The greater the variance, the more spread out the distribution would be. On the other hand, the more concentrated a distribution is around its mean, the smaller the variance. Now, the variance has as units of measurement the square of the units of measurement of the original random variable. And sometimes, that can be confusing in terms of how to interpret that, right? And so we might like a measure of variability that has the same units as the original random variable. Now, one way to obtain that would be to take the variance, which has units that are the square of the original random variable, and then just take the square root of the variance. Now, remember, when we do that, we would have to calculate or take the square root of the units as well. And so in doing that, we would get a measure that has units that are the same as the units of the original data. And that quantity that we've come up with, that we've just talked about, the square root of the variance, is the standard deviation for the distribution, or equivalently, the standard deviation of the random variable x. And so again, let x be a random variable. The standard deviation of x, or of its distribution, will be denoted in a couple ways. We might denote it as capital S, capital D of x, so standard deviation of x. But we'll also use this notation, the lowercase Greek sigma, all right, the S sound for standard deviation. And it's defined to be the square root, the positive square root of the variance. And so we could write it either as the square root of sigma squared, or as the square root of var of x. So either way is fine, all right? But that's how it's defined. So this is another measure of the variability or dispersion, how spread out a distribution is, or equivalently, how variable a random variable is. And it has the advantage over the variance of having the same units as the original random variable. Now, is there any way to interpret the standard deviation, the population standard deviation, or the standard deviation in general, whether we're talking about a population standard deviation or a sample standard deviation? So we're talking about the standard deviation in general, all right? So there are a few ways, a few very helpful ways actually, that we can interpret the the standard deviation. The first that we'll look at is the empirical rule. Now, if a distribution is unimodal and symmetric, right? Remember, unimodal means that it's got one peak, and then symmetric means that the right-hand side is a mirror image of the left-hand side, about a vertical line through the location of the mean. And so what we're really talking about here is some kind of a bell-shaped curve, much like the normal distribution, although that's not the only bell-shaped curve. There are many different kinds of bell-shaped curves. All right, so if the distribution of a random variable is unimodal and symmetric, that is, if it has a roughly bell-shaped curve, then we know the following. It turns out that approximately 68% of the values in the sample space of that random variable, I'll be more clear about that in a second, but approximately 68% of the values will lie within one standard deviation of the mean. In addition, approximately 95% of the values will lie within two standard deviations of the mean. And then finally, nearly all of the values will lie within three standard deviations of the mean. So this gives us some very useful information about the probability structure, the probabilities that a random variable takes on over certain portions of its sample space in the vicinity of the mean. And so here is, let me see here, let me advance the slide. So here are some plots showing this, or graphs showing this. So this is a graph of a normal distribution. I created this on my TI-84 calculator software that I use. And what this shows, all right, so we have a bell-shaped curve, and in particular, this is a normal distribution. And this distribution has a mean of 0, right? So 0 is located right here, and it has a standard deviation of 1. Now, if we go out one standard deviation on either side of the mean, which is 0, so if we consider the interval from -1 up to +1, so it's an interval that's centered at 0, the mean of the distribution, and we're going out one standard deviation on either side of that mean, then we can see here that remember that area under a PDF or under a PMF, whichever, corresponds to the probability that the random variable takes on a value in the interval over which we have shading. And so what this is telling us graphically is that the probability that a random variable possessing this distribution takes on a value from -1 up to +1 is 0.68269. So that's about 0.68, which is what the empirical rule said. Now, if we go out one more standard deviation, so 2 standard deviations on either side of the mean, which is 0. So again, what we're considering here would be the interval from -2 up to +2. Then what is the probability that a random variable possessing this distribution would take on a value somewhere in the interval from -2 up to +2? And the answer is 0.9545. For this particular distribution, for this normal distribution, the probability would be 0.9545 rounded to 4 decimal places. Well, that's approximately 95%, 0.95, isn't it? And then finally, if we got one more standard deviation, so we're looking at 3 standard deviations on either side of the mean. So let me show that. So we can see here that the probability that a random variable with this distribution takes on a value somewhere on the interval from -3 up to +3 is 0.9973. And that's about all of the probability, isn't it? Because the total probability is 1. So that is where, that's really where the empirical rule comes from, right? If we're dealing with a distribution that is bell-shaped and so therefore approximately normally distributed, then we're going to have these results. Now, what if we're dealing with a distribution that is not symmetric? It's not bell-shaped, all right? So perhaps it's got a lot of asymmetry, maybe a lot of skewness. And so, for example, if we're analyzing income data, as an example, then income data tends to be right skewed. Some people make or have a whole lot of data. a whole lot of money, a very high income. Other people, most of us, have, something much, much smaller. And so anyway, and plus there's a natural boundary at 0. And that natural, whenever you have a distribution with a natural boundary at 0 or some other boundary, then that often induces asymmetry or skewness as well. So, what if we're dealing with a distribution like that, right? So that really the assumption contained in the empirical rule is not satisfied. Well, there is another result that applies even in that situation, and this is called Chebyshev's rule. Chebyshev was a Russian mathematician, probabilist, and anyway, he came up with this, and Chebyshev's rule says that for any distribution, not just a bell-shaped curve, but for any distribution, at least 1 minus 1 over k squared times 100% of the values in the sample space of that distribution will lie within k standard deviations of the mean. And in order for this to be greater than 0, k has to be greater than 1, obviously. So it could be 2, 3, 4, 5, or we could look at fractional value, 1.2, 1.5, whatever. All right. Now, to look at some particular values for any distribution, regardless of shape. So even if it's very skewed, Chebyshev's rule tells us that at least 75% of the values will lie within 2 standard deviations of the mean. At least 88.9% will lie within 3 standard deviations of the mean. And at least 93.75% will lie within 4 standard deviations of the mean. One thing I want to point out is that we're not saying approximately here, and we're also saying at least. And so what we've got here are lower bounds on the probability that a random variable will be within a certain number of standard deviations of its mean. And so, as an example, let's consider a particular non-bell-shaped curve, and in particular, a right-skewed distribution. Consider the chi-square distribution with 1 degree of freedom. Now, this is a highly right-skewed distribution, and it's very heavy-tailed. All right. In addition, the mean of this distribution is 1. The variance of the distribution is 2, and the standard deviation would therefore be the square root of 2. Now, according to Chebyshev's rule, the probability that the random variable x, which has this chi-square distribution with 1 degree of freedom, the probability that x takes on a value that is within 2 standard deviations of the mean would be at least 0.75 or 75%, and the probability that it takes on a value within 3 standard deviations of the mean would be at least 0.899. So that's interesting. It's interesting because this is a skewed, very right-skewed distribution. Again, it's a highly right-skewed distribution with very heavy tails. Right? And so the question is, how do these lower bounds, 0.75 and 0.889, which apply for any distribution, how do these lower bounds compare with the actual probabilities for this particular chi-square distribution? Because we're dealing with a known distribution here, chi-square distribution with 1 degree of freedom, we can actually calculate what these probabilities would be. All right, and so once we do that, we can compare with the guaranteed lower bounds. And so here is a picture of the chi-square distribution with 1 degree of freedom, and the mean of this distribution is 1, so it's located right here. All right. And then what we're doing is looking at the probability that the random variable takes on a value within 2 standard deviations of the mean. Now, because this distribution does not have any support to the left of 0, when we go 2 standard deviations to the left, there's no probability to the left of 0, and so we can stop at 0. But then to go to the right 2 standard deviations, we go, let's see, so this would be about 1 standard deviation, and then that point right there corresponds to 2 standard deviations to the right of the mean, which is 1. Okay? And so anyway, the probability that x, this chi-square this chi-square random variable with 1 degree of freedom takes on a value over that interval is 0.94961. If we go out 3 standard deviations on either side, then obviously, again, we stop at 0 here, but we go out to 5.24264, which is about right there. Okay, that would be 3 standard deviations to the right of the mean of 1. And that probability is 0.97796. So that is what we have here. The actual probabilities for this highly right-skewed, heavy-tailed distribution are that the probability that x takes on a value within 2 standard deviations of its mean is 0.94961, and the probability that it takes on a value within 3 standard deviations of the mean is 0.97796. 0.96. Now, both of these probabilities are much greater than the guaranteed lower bounds of 0.75 and 0.889 respectively that are provided by Chebyshev's theorem. Remember that Chebyshev's theorem says that this probability is going to be at least 0.75, and it is, but it's a lot bigger than that. And Chebyshev's also tells us that the probability that x takes on a value within 3 standard deviations of its mean will be 0.889, and we can see here that that is in fact the case. And again, 0.97796 is quite a bit larger than that guaranteed lower bound. So we see that the lower bounds that are provided, that are guaranteed by Chebyshev's rule, are very conservative, and also that the empirical rule can even provide reasonable approximations to these probabilities for distributions that are highly right-skewed and very heavy-tailed, because remember what the empirical rule said. The empirical rule said, that if you go out 2 standard deviations, and we're dealing, if we were, and this specifically applies to a bell-shaped curve, but if you go out 2 standard deviations, you're going to capture about 95% of the probability. Well, even though this is a highly right-skewed distribution, look, that's, for all intents and purposes, that's 0.95, isn't it? And it also tells us that if we go out 2 standard deviations, I'm sorry, it said 68%. Well, that was one. I'm sorry, that was 1 standard. 2 is 95%, and then if we go out 3, we capture virtually all of the probability. Well, look, that's it's a little bit less than 0.997, but that's still a lot, about 0.98. So that's almost all of the probability. So what we see here is that there are some right-skewed distributions that the empirical rule will actually give us fairly accurate approximations to these probabilities. So Chebyshev's rule always applies, but because it always applies, it's going to be conservative. Those lower bounds that it gives are going to be conservative and may be very conservative. We know that the empirical rule applies when we have a bell-shaped curve, but it also is fairly applicable even if the distribution is not that bell-shaped, as we're seeing here. So this is a good place to stop this particular lecture video. We will pick up the next topic in the next lecture video.